In this first unit of the next chapter, what we're looking at is graphing equations. And so there's a variety of ways that we can approach graphing. The most rudimentary, the brute force approach, is to just use a table like the one that we see here, plug in values for x to generate outputs for y, and then figure out what the trend is of those points, hopefully use a little previous knowledge to inform us as well. And then we end up with a graph, which is basically a picture of all of the points that work in that equation. So for the example that we have here, we've got this t-table. So I'm going to try to use input values that are balanced around the origin. I don't want to go too far out from the origin because I don't want to have to make a giant graph. So I'm just going to pick some negatives, plug in 0, plug in some positives. And so I just plug the inputs in for x to figure out what the outputs are. So to start off with, we've got -2 for x. So we've got -3 times -2 gives us 6. 6 plus 5 gives us 11. And so then I can go back 2, up 11. So I'm just off my graph here with a dot right up out there. If I plug in -1 for x, we get -3 times -1 is 3 plus 5 gives us 8. So again, we can go ahead and plot that point as well. Then we can just continue. If we plug in 0 for x, hopefully it's obvious that we get an output of 5. And we should be familiar with this type of equation. It's written in slope-intercept form, so we probably could have graphed it without having to use a t-table. But if we continue the pattern here, plug in 1, we get out 2. If we plug in 2, we get out -1. So we can plot those last couple of points here and here. And so now we can draw the line that represents all of the infinite solutions of that particular equation. In the next one here, we can kind of do the same thing, use some similar points here, -2, -1, 0, 1, and 2. Then we can plug those values in for x and then generate the outputs again. Now we should be careful here when we see -x squared plus 4. We should think of this as -1 times x squared plus 4. So we have a little order of operations that we have to perform. We're going to square our input first, and then we're going to multiply it by the -1, and then we're going to add 4. So if we plug in -2 for x, -2 squared is 4. 4 times -1, -4. -4 plus 4 gives us an output of 0. If we plug in -1 for x, again, have to square it first, so we get +1, but then we hit it with that negative right away to make -1. -1 plus 4 gives us 3. So I'm left 1, whoops, try that again, and up 3. If we plug in 0, so we're going to get 0 plus 4, so we're going to get 4. And if we plug in +1, we're going to end up with the same result as when we plugged in -1. Plug in 1, we square it, we get 1, but then we hit it with the negative that's out front, so we get -1. -1 plus 4 gives us 3. And so hopefully it's not too big of a surprise that we're going to end up repeating the same value as we had for -2 when we plug in +2. 2 squared is 4, make it -4. -4 plus 4 indeed gives us 0. So if we look at the points that we've plotted, hopefully it's not a surprise that we did not end up with a straight line graph on this one, but instead we ended up with a curve called a parabola. So whenever we have an equation where the highest exponent of x in that equation is squared, we're going to end up with a vertical or a vertically oriented U-shaped graph. So this one is opening down as a result of that negative sign in front of the x squared. If it was a positive number, it would be opening up. But we do end up with a parabola whenever we have this x squared as our highest exponent. In the first two examples, just going with -2, -1, 0, 1, and 2 as our x values worked out fine for us. In the first one, it gave us enough information because the graph was simple as a straight line. On the second one, it worked out for us because it just so happened that our parabola was centered on the y-axis. So having inputs balanced around the number 0 was going to give us a very good picture of the graph. But if our parabola had been over here, let's say, centered over there closer to 10 as opposed to 0, we would not have seen the U shape of our graph. So this reveals some limitations to the process of plugging in just any old values for x, or just using the same -2 through 2 as our inputs. We might not capture the essential information about our graph. And that's true for this next one here. So we want to probably use a little bit of thinking ahead, to a little forethought, to try to determine what numbers we should plug in for x. If we think about back to our brief discussion of domain of functions in the previous chapter, at the tail end of the previous chapter, we looked at square root functions as being a place where we had exceptions to the rule of a domain of all real numbers. So in this circumstance, we can't take the square root of a negative number, so we're going to have a limitation there. So our technique to figure out what that domain would be was to take, oops, try that again, to take x plus 6, or whatever is underneath the square root symbol, set it greater than or equal to 0, and then solve from there to figure out what our domain is. Well, if we do that here, we're going to get x is greater than or equal to -6, meaning that -6 is the smallest number that we could plug in for x into this function. And when we do that, -6 plus 6 is 0, the square root of 0 is 0, and so we've got a point here at 1, 2, 3, 4, 5, 6, 0, -6, 0 on our x-axis. But then from there, we don't just want to go up by ones necessarily, because we would like to be able to plug in numbers that are going to be a little bit user-friendly. I don't want to have to break out a calculator if I can avoid it. Now, if I plug in -5, that's not going to be too bad for us, because -5 plus 6 is 1, which is a perfect square. So when I take the square root of that, I get 1 as an output. So back 5, up 1. But if I go -4, I'm going to get 2 underneath the square root symbol, which is not going to be user-friendly. The square root of 2 is 1.41-ish. And so for plotting this on the graph that I have in front of me, it's not going to be terribly helpful. So instead, I want to try to figure out what value of x I need to plug in so I hit the next perfect square. So my first number I plugged in, -6, made 0 underneath the square root symbol. -5 gave me 1. So the next perfect square is 4. So that means I should plug in -2 for x. -2 plus 6 is 4. The square root of 4 is 2. So I'm left 2, up, now I'm 2, so right about there. So I'm just trying to use a little strategery to give me the best option, or best opportunity to keep the problem simple. So 0 is a perfect square, 1 is a perfect square, 4 is a perfect square. So the next perfect square is 9. So what do I need to plug in for x here so that I'll end up with 9 underneath the square root symbol? Well, that's going to be 3. So 3 plus 6 is 9. Square root of 9 is 3. So I'm over 3, up 3. And so again, we can see that we've got a graph that's not linear. It's not a U-shape like it was on the previous one, although it is related to a parabola. What we have is half of a sideways parabola. And so the general shape of any square root function is going to be along these lines, half of a parabola laying on its side. Now, one thing I'll point out is a lot of times we'll fall into the trap of thinking that it should be plus or minus there, so I should be getting points down here as well. But if we think a little bit about that, that would mean that we would not have a function. It would fail the vertical line test. We'll discuss that more in more depth later. Just because we see a square root symbol, even though we know that there's another square root out there that's the negative answer for all of these outputs that we generated, in this circumstance we're only going to take the principal root. We're not going to take the negative root to go along with the positive root. And so that's why these points are not included in our graph, and we just get that half of a sideways parabola.